All right, we'll get going. Before we start really getting into modeling and investments, there are a couple topics I want to review with you. They're probably topics that you're pretty comfortable with. We've done these kinds of things a lot. I just want to make sure we're really comfortable with them before we get into something new. The first of those is evaluating expressions, which is essentially if we have an expression and we just want to plug a number in and simplify. For example, if we have 12x plus 180 and we want to plug in the idea that x equals 8. So, what would this expression over here equal if we know x is equal to 8? When we do that, we're just going to take that 8 and plug it in where the x is. And so we'll have 12 times 8 plus 180. When we plug numbers in, it's kind of a nice thing to use parentheses to help keep things organized. If it were a negative, we wouldn't lose track of the negative. If we put those parentheses in there, we wouldn't get confused and think it was subtraction. By the parentheses sort of help everything stay organized. And here it's just we're putting an 8 in where the x was, and we're going to simplify what we have over here on the left. And we have to remember order of operations. Please excuse my dear Aunt Sally. We have parentheses, but there's nothing to do in those parentheses, so that's done. There aren't any exponents, so there's nothing there. Now we do multiplication and division, left to right. And so what that means is we're going to do this multiplying over here before we add. So the first thing we'll do here is that 12 times 8 and get 96 that we need to add to 180. And then we'll add those two together and end up with 276. Basically, what we're doing here is we're making sure we're careful when we plug in for a known value and then following order of operations when we simplify to get to our final result. You let me know if you have questions on any of that. My guess is most of it's comfortable, but if there's anything that's rusty or you're just not sure of, you can absolutely ask. Up next for review, the idea of solving equations. And, we've gotten fairly comfortable with this, I think, in a lot of different contexts, whether it's geometry or consumer math. But it never hurts to sort of refresh our memories a little bit. Whenever we're solving an equation, the main idea is we want to know what value of that variable would make the equation true. What is it that we could plug in there to make this be a true statement? Trial and error could work, but that could be clumsy and take a long time. So instead we use algebra. And when we're using algebra, we're trying to get this x by itself. So we want the term with x by itself. So when we look at that left-hand side of the equation there, we're going to peel that onion from the outside in. The first thing we're going to get rid of is the 180. Then we're going to get rid of the 12, and that's how we're going to leave the x by itself. This says 12x plus 180. What am I going to do to make plus 180 go away? What's the operation I'll do there? As I work to get rid of that 180 on the left-hand side, I have to do something. What is it I'm going to do to get rid of that plus 180? Perfect, Jenny. Thank you very much. I'm going to subtract 180 on the left so that those cancel. If I subtract 180 on the left, I'm going to subtract 180 on the right. And my guess is that most of you have gotten pretty comfortable with this by now. And so it's like, yeah, we know. Well, I know you know, but I want to ask you anyway, just to sort of reinforce it over and over again. On the left-hand side, that leaves us 12x, which means 12 times x. And on the right-hand side, we have whatever 384 minus 180 is, which is 204. So based on what I said a minute ago, I know you know, but I'm going to ask you anyway. Now I'm trying to get that x by itself. This is 12 times x. What am I going to do to get rid of 12 times x to get that x by itself? Perfect, Jenny. That's it. And Jessica, I think, is coming in right behind you with the same thing. Maybe, maybe not. We'll see. Okay, very good. You could have typed it in there, Jessica. That would have been all right. We're going to divide by 12 on the left so that those cancel, leaving just the x. And when we do that, we better divide by 12 on the right side also. And what happens then is I just have x on the left, which is what I was after. 204 divided by 12 on the right is 17. And so we have solved that equation to find out that x is 17. What this means is, when solving an equation, what it means is if we wanted to put something here for x and have this be a true statement, that something that we would have to put there would be 17. So that's what solving an equation does. It's what would make the equation true? Well, if x were 17, that would make this equation true. Okay, now we'll go and talk about modeling a little bit. So what mathematical modeling is using some sort of function or equation that represents a real life situation. So we have some real life situation that we'd like to represent with an equation, and making a model is, we describe that process as making a model. I'm going to make a model for this situation. All right, go ahead then. Make an equation that represents it. And as far as we are concerned, function is essentially just sort of a fancier name for equation. You may have seen functions written as f of x equals somewhere along the way. We're not going to do that kind of stuff here. We're just going to be focused on writing equations that represent a real world situations so we can work with them. Two types of models that we are going to be concerned with are linear models. And linear models are exactly what you would think. If you were to graph it, it would make a line. And exponential models, where if we were to graph it, it would make a curve. When we talk about linear models, we can talk about linear growth, meaning the line would go up from left to right, or linear decay, meaning it would go down from left to right. We could talk about exponential growth, meaning it goes up from left to right. We could talk about exponential decay, meaning it goes down from left to right. We'll get into more specific equations in a little bit, but for right now, linear models make a line, exponential models make a curve when we graph them. Go ahead and look at our first linear model. One thing that's important to note about linear models, and well, how can I tell if it's linear or exponential? That'd be an excellent question for you to have. And the way you can tell is by looking at the equation itself. A linear model, it's going to have a variable in it somewhere, and that variable is not in the exponent. There are no variables in the exponent in a linear model. There might not even be an exponent at all. There's definitely not any variables in the exponent. That's how we know it's a linear model. A pizza parlor charges $10 for a large cheese pizza plus an additional $1.50 per topping. If we wanted to write a model for the cost of a pizza at this particular establishment, we could say that, well, the cost of the pizza is going to be, well, it's $10 right away, and then on top of that, we have to add $1.50 for every topping. So $1.50 multiplied by the number of toppings. We just made a linear model. Linear modeling, mathematical modeling can sound like a very sort of, I don't know, challenging, difficult kind of topic. But honestly, all we're doing is creating an equation that represents a real world situation. And we've done that here. If I multiply $1.50 times the number of toppings plus the $10 just for a cheese pizza, that gives me the total cost. I have created a mathematical model. This is a model for the situation for how much would a pizza cost at this particular pizza place. And we'll look at models that are more involved than that, but at its heart, that's what modeling is. Come up with an equation that represents a real world situation. We can use models like this to answer questions. Here's a poll for you. This pizza parlor that charges $10 for a large cheese and $1.50 per topping, find the cost for a pizza with 3 toppings. I'll make a poll for this, and you can let me know. So what would a 3-topping pizza cost at this particular place? Given the idea that they charge $10 for the pizza with nothing on it, plus $1.50 per topping. Essentially what we're doing here is, once we have a model, can we use it? This is an example of linear growth, because the more toppings you have, the more expensive the pizza is. So the price goes up as the toppings go up, and that's why it's growth. We'll look at how it's linear in just 1 second. We'll go another, let's say 15 seconds, and then talk about this one. Let's see where we are on this one. Okay, not unanimous, but definitely strong agreement. That's very good. So we're working with the same model we saw just a minute ago here, where the cost of our pizza is $10 plus $1.50 per topping. If you're not sure if it's linear or exponential, because that's kind of a new idea for us at this point, when we look at this, there's no exponent anywhere around. There's no exponent at all. We certainly don't have a variable that's in the exponent, and that's how we know that this is a linear model. If we were to graph it, it would make a line. In this particular case, we have a 3-topping pizza, so our cost is going to be 10 plus $1.50 times 3. All we've done is put 3 in for t because we know there's 3 toppings. Now we have to follow order of operations. Multiply first. So 3 times $1.50 is $4.50. And then we add to end up with a total cost of $14.50. Let me know if you have questions on that. Went pretty well. So I think we're probably comfortable, but if you have questions, you let me know. Okay, another problem involving linear growth. A widget factory costs $1,400 per month to operate, and the materials for producing one widget costs $18. So it's $1,400 to operate, and then to make a widget costs $18. To the nearest whole number, how many widgets could be produced in a month for $7,000? What we're going to want to do here is come up with a model for our total cost. So let's start with that. The total cost of operating this factory is, well, let's see, it's $1,400 a month plus making a widget costs $18. So this is very similar to the pizza question. The pizza question was $10 for a large, $1.50 to add a topping. This one is $1,400 to keep the doors open, and then $18 for every widget. So we have to multiply 18 times the number of widgets to get that cost. We add it to the 1,400, and that gives us our total cost. If you don't see where that model came from, let me know, but this is a model of this situation. We can see there's no exponents anywhere, so it's linear model. Now this one's a little bit different. This didn't say how much would it cost if you made 1,000 widgets. It said how many widgets can be produced if your total cost is $7,000. So if all you have is a budget of $7,000, how many widgets could you make? So this time we're trying to find W. So we're going to have to solve an equation here. All right, well, the total cost, the budget I have is $7,000. And that's 1,400 plus $18 per widget. So I have this equation over here that I need to solve for W. I'm trying to solve for W. I need the term with W by itself. I'm going to peel this onion from the outside in. I'm going to start by getting rid of that 1,400, and we'll do so by subtracting that from both sides. If you see something that you're not sure why we did it, or you're not sure where the numbers came from, please make sure you ask. Those will cancel, leaving 18W on the right-hand side, and on the left, 7,000 minus 1,400 is 5,600. Got 18 times W, just like we saw when we were reviewing our solving equations. I'm going to divide by 18 to make that go away. Those cancel, and that leaves me with W on the left, or excuse me, on the right, and 5,600 divided by 18 is 311.111, and that keeps going. At this point, I'm done with all my calculations. I go back and say, were there any instructions on how to round here to the nearest whole number? I can either make a whole widget or not. I can't make half of one. Widget's just a fictitious, we've got a factory over there. It makes widgets. We don't know what they are. There's just one of those words you can use as kind of a placeholder. So to the nearest whole number, so that's the ones place. We look one space to the right, 4 lower, so we round this down. And if I had $7,000 to spend, I could make 311 widgets without going over budget. The main thing here was this. First, we set up a model that represented the total cost. And then, unlike before where we just kind of plugged in, this time we had to do a little algebra to solve the equation to figure out how many widgets it would be. Are there any questions on anything we did there in setting up the model or solving the equation? All right, I'm gonna have you make a model. A box of dry cat food contains 60 ounces of cat food. Each day, the owner uses 2 ounces of food to feed their cats. Write a linear model that gives the amount of food remaining after X days. So what we're trying to come up with here is it's your job now to come up with the model. And we want that model to work for any number of days. We want to be able to plug in 1 for X, 2 for X, 5 for X. We want the model to work no matter how many days it is. That's what X is going to represent. All right, I'll give you a sum to look at here, and you can tell me what the model would be. And we're after a linear model, so none of our choices are going to have a variable in the exponent because that would be an exponential model, and we want a linear model. This is the amount of food in the box is going to go down at a consistent level. That's why this is linear decay, because What we're seeing here is the amount of food that remains, and that goes down over time. So that's why it's linear decay rather than being linear growth. Sometimes creating the model is a little more challenging than just using a model. When we know what the model is, okay, I'll answer your question. Coming up with the model can be a little more challenging, and that's what we're working on here is coming up with a model that would represent this real world situation. Sometimes I'll say, if you come up with an answer and it's not one of the ones shown, um, pick the one that's closest. This isn't really one of those times. I can tell you the one we're looking for is in there. And I hope it's the one that jumps out to you as the correct choice. We'll go another 30 seconds and then talk about this. All right, let's see where we are. Not unanimous, but strong agreement. That's good. Okay, so let's take a look here and see how we make this model. If you're not sure, if something doesn't make sense, you let me know. But the idea here is basically this. The amount of food that remains, well, we're starting with 60 ounces of food, and we're going to use 2 ounces per day. So we're using it, so we're subtracting. So the amount of food in the container is going to get lower and lower and lower because we're subtracting. And then they use 2 ounces per day. So we want to take 2 ounces and multiply that by the number of days. That's how much food, this is how much food they've used. If we subtract that from how much there was when they started, we wind up with how much food's left, and there's our model that gives us the amount of food that remains after X days. After 3 days, we'd plug a 3 in. After 12 days, we'd plug a 12 in, and so on. Let me know if you have questions about coming up with that model or how it would work. An example of using it would be this. A box of dry cat food contains 60 ounces of food. Each day, the cat owner used 2 ounces of food to feed their cats. How much food would remain after 18 days? We'd start out here by creating that model. The amount of food that remains is 60 minus 2x, where x is the number of days. And if we want to know how much is left after 18 days, then we're going to have to do 60 minus 2 times 18. And again, we're going to follow order of operations when we simplify this. We have subtraction and multiplication. So we're going to do that multiplication first. And we'll have 60 minus 36, which is 24. So how much food would remain after 18 days? 24 ounces. And essentially, this is the process of creating and then using a mathematical model. Before we get into exponential decay, I want to see if anybody has any questions about what we've worked on so far, talking about linear or linear growth, linear decay, making a model, using a model. If anybody has questions about any of that, let me know. All right. Up next will be exponential modeling. Before we get there, though, I want to talk about growth rates. Let's say that Debbie makes $2,000 per month and she's going to receive an 8% raise. What would her new monthly pay be? Well, follow along with me here and let me know if you see something that is confusing at all. But so she makes 2,000 now, and we need to add to that whatever her raise is going to be. If we want her new monthly pay, we're going to start with here's what she makes now, and we're going to add on top of that. So, and we're going to add 8% of the $2,000 that she makes right now. So, what we're doing here is we're taking her current pay and we're adding 8% of that pay. So far, so good. We'll go ahead and figure out the numbers here. So 2,000 plus, let's see, we'll go back and we'll say we did percents. We did great with percents. That'll be 8% of is multiply 2,000. So the 2,000 that she makes now plus whatever 8% of 2,000 is, 0.08 times 2,000. That's $160 that she's going to get in a raise. And we'll add those together, and her new pay is going to be $2,160. Let me know if that makes sense to you. What I'm going to do is I'm going to answer this same question in a little bit more of an abstract way. I kind of touched on it there just a second ago where I said what we're doing is we're taking her pay and we're adding 8% of her pay. So it's whatever her pay is now plus 8% of that pay. So let's see, if that's her pay now plus 8% of her pay. So it's P plus 0.08P. Back to algebra a little bit. Does anybody remember? If we don't put a coefficient here in front of a number, what number is there? We just don't bother to write it. What number is really here? We just don't write it down. If you don't remember, that's okay. Oh, very good, Kevin. Thanks. Perfect. Yeah, there's a 1 here. We just don't write it down. That's 1 times P, because multiplying by 1 doesn't change it. It's still just P. All right, so if I'm working on Debbie's salary increase over here, and I have 1P plus 0.08P, well, I could add those together then. Those are like terms. I've got 1P plus 0.08P. If I put those together, that's just 1.08 times P. And so what's happening here is this. We started out with some salary. We added 8% on top of that. And when we're done, we get 108% of what that pay used to be. Just to make sure that this works for you. So let's see. I could do it this way to find out what her new pay is. But you know what? If she's going to get an 8% raise, then her new pay is going to be 1.08 times her old pay. So instead of doing all of this, I could have just done 1.08 multiplied by her salary. Let's see if that works out. 1.08 times her $2,000 salary. Sure enough, look at that. That's 2,160, and I went straight to it. Because she was getting an 8% raise, her new pay is going to be 1.08 times her old pay. Please let me know if that doesn't make sense. It's going to be really helpful going forward if that feels comfortable for you. And how we got there was we said, well, here's her old pay. If we add on 8%, then we've got one whole salary. Add on 0.08. Now it's 1 plus 0.08. That's 1.08. Or this is 108% of her old salary is what her new salary is going to be. And so multiplying by 1.08, that just gives us her new salary. If that's comfortable for you, that's fantastic. If it's not, please let me know, because we're going to use that concept, this concept over here, as we go forward. Okay, outstanding. Let's talk about making an exponential model. We talked about linear models do not have a variable in the exponent. A nice thing about exponential models, they're easy to identify because they do have at least one variable in the exponent. You might be thinking, well, what the heck would that even look like? Well, you're very familiar with an exponential model already. It looks like this. The formula for compound interest. What you'll notice in that formula for compound interest is we have variables that are in the exponent. And so you've already worked with an exponential model, you just didn't know it. Compound interest is a model that has a variable in the exponent. We're going to see some others, but that's one example that you're already familiar with. But keep in mind, an exponential model has a variable in the exponent. And here's an example of one of those. The population of a town is 6,000 people, and it's growing by 3% each year. That population growth is modeled by this equation right here. I want to talk about that a little bit. So the population is 6,000 and it grows by 3% every year. So let's just look at 1 year real quick, the very first year. So I'm starting out with 6,000 people in my town and it grows by 3%. Well, just like Debbie's salary, if it grows by 3%, then the new population is going to be 103% of the old population. So what I'm going to need to do here is I'm going to need to multiply that by 1.08, and that'll give me my new population. You know, whatever that would be, 6,000 times 1.08, my new population would be 6,480. The 6,480 is not that critical. That's just after 1 year. What's important here, what I want you to recognize, the main thing I want you to see is because, oh, I put 1.08. How about 1.03? I apologize. 6,000 times 1.03. Somebody should have caught me on that. 6180. All right, I'm going to read that again. I'm going to say it again so that it makes sense since I wrote the wrong numbers down. Population of a town is 6,000. It's growing by 3% every year. That means at the end of a year, the new population is going to be 103% of the old population. In the same way that we found Debbie's new salary, we can find a new population of the town. Take the 6,000, multiply by 1.03, and we get 103% of the old population. I apologize for that. I'd say typo, except I wrote the number down. So it was more of a right O. So we can multiply by 1.03 to get the next year's population. And so if I want the population of this town after 1 year, I can multiply by 1.03. If I want the population after 2 years, though, now I need to multiply by 1.03 again. And if I want the population after 3 years, I need to multiply by 1.03 again. And that's how this model gets built. What we're doing here is we're saying, okay, you're starting out with a population of 6,000. The growth is 3%. So your multiplier, the thing you're going to multiply by each time then is going to be 1.03. That's how it gets 3% bigger. And then the number of times you multiply by 1.03 is just however many years you want to look into the future. 1 year into the future, just multiply by it once. 5 years into the future, you want to multiply by it 5 times. 20 years in the future, you want to multiply by it 20 times. And that's why we use an exponent here, is because we're multiplying by 1.03 over and over and over again. And so that's where that exponent comes into play in this model. Let me know if you have questions on how we arrived at this model before I go forward. The main idea there is the growth rate is 3%, so we use 1.03 when we make our model. So our starting amount times our growth rate raised to the n power, and n is the number of years. All right, you try one. The population of a town is 2,500. It's growing by 5% each year. What will the population of this town be after 6 years? So we're using the ideas that we saw in Debbie's salary increase to get our growth rate. That's going to be our multiplier. We have our starting population, we have our multiplier, and we know how many years it is. So that's going to be our exponent. I'm going to go ahead and set up the poll for this and we'll try it. Okay, so in this one, we have to think about our starting population, our growth rate, and how many years. So it's not necessarily a question that takes very long to do, but you have to be careful in how you set up your model. That's the challenging part of this one, is setting up the model. And then remembering back to compound interest and using our raise any number to any power button, our x to the y to the x, or caret. That key on our calculator is important here. Let's go another 20 seconds. If you need more time, you can let me know. But we'll go 20 more seconds and then talk about this if everybody's ready. I do think coming up with the model is the most challenging part of this one. Okay, let's take a look. Oh, and it's definitely a type of question you can expect to see in homework and quizzes and exams. Okay, strong agreement. Not everybody responded on this one. Maybe got a little stuck, so we'll talk about it carefully. But those of you who did answer, definitely some strong agreement there. That's good news. All right, so the population is 2,500, growing by 5% each year. What will the population be after 6 years? So our future population will be 2,500 to start with, multiplied by, if it's growing by 5% each year, then the new population is going to be 105% of the old population, which when we write that as a decimal is going to be 1.05. That's our growth rate, our 1.05. And what will the population be after 6 years? Well, I want to multiply by 1.05 6 times because it's going to grow every year by that much. So I want to raise that to the 6th power. The hardest part of this question, I believe, is setting up the model. And there's our model. It's essentially, how many people do we start with? What's our growth rate? How many years are we looking down the road? So that's our setup for our model. Now we're going to use order of operations. We've got to do the exponent first. We'll have 2,500 times whatever 1.05 to the 6 is, which is 1.3400, and that keeps going. And then I only have one step left to go, and that's multiply that by the 2,500 and end up with 3,350.239. But we're talking about people here. We can't have a fraction of a person or a decimal of a person, so we round this to the nearest whole number. And when we round to the nearest whole number, that's the ones place. That's 4 or lower, so we round this down to 3,350. So our new population after 6 years will be 3,350. Okay, Jenny, the key with that 5% becoming 105% is because we're growing by 5% each year, which means our population is starting from here and getting bigger. So it's starting from 2,500 and getting bigger by 5%. So we have the original population, whatever it is, plus 5% of that population. So this is how we get our growth rate. And it's what we did with Debbie's salary increase. These are the people, this is the initial population. Here's our 5% growth. And so what we have then is we have 1 times the population plus 5% of the population. And when we add that together, what we have then is we have 1 times the population plus 5% of the population. And now these are like terms. We have 1 plus 0.05. We add those together, and that's where the 1.05 comes from. Essentially, what we're saying is after that year of growth, the new population is going to be 105% of the old population. Outstanding. So the new population will be 105% of the old population. It's the original population plus 5% more. So 105% of the old one. Outstanding. Very good. That's the hardest part of these, Jenny. It's not, that is what gives students trouble here. And so my guess is you're not the only one with that question. And I'm really glad you asked it. That's how exponential growth works when we've got a model. And you might be asked to make the model, but the model would be along these lines where we know what the growth is. So we find our growth rate, and then we use that when we build our model. Looking at an example of exponential decay. 20 milligrams of a radioactive isotope is decaying, and it's modeled by the function shown there, where n is the amount of isotope remaining after t hours. The first thing I want you to do here is take a breath. You're not going to have to do any chemistry. You're not going to have to know any chemistry, and you're not going to have to create a model like this one. You may definitely be asked to create a model about population growth, like the one we just looked at. But a model like this one, this is the kind of thing that even if you were in a chemistry class, you'd look it up in the book. You wouldn't create it on your own. You're not going to be asked to create a model like this one. You will have to be able to use a model like this one, though. And so if we start out with 20 milligrams of an isotope and it's decaying, we can see it's decaying because this number is smaller than 1. Again, you don't have to know that, but if you happen to notice it, that's absolutely the truth. If the number in here is bigger than 1, like it was in our population growth, we have growth. If the number in there is smaller than 1, then we have decay. And just like it was with the population question, this is our starting amount right there. And then this is going to be, how many times are you looking at it? With our population question, it was years. In this particular radioactive isotope situation, it's about hours. So it decays pretty fast. But it's how many times are you checking is what that exponent's going to be. And so here we have this model for radioactive decay of an isotope. And then we might have a question to answer about it that is rounded to the nearest tenth. How many milligrams remain after 11 hours? So given this model, so you didn't have to create this one. It's been given to you. How many milligrams remain after 11 hours? So this is just about, can you use this model to figure out the number of milligrams that remain after 11 hours? I'll set up a poll for this and you can try it. I think the challenging part of the last one was writing the model. The challenging part of this one, well, if writing the model is the hard part, that's already done. We just have to use it. So now this is more about making sure you follow order of operations properly, making sure you know how to use the raise any number to any power button on your calculator properly. And on this one, if you come up with a number that's not shown there, you pick the one that's closest to yours, so I know you've had enough time to try it. We'll go another 30 seconds and then do this one together. If you need more time, just let me know. Let's see where we are. Unanimous. Outstanding. That's great news. Okay, good, good. So we're very comfortable working on evaluating a function involving an exponential model. That's great news. So here we have the amount that remains after 11 hours will be 20 times 0.951 raised to the 11th power. Order of operations, we've got to do that exponent first, which will be 0.951 raised to the 11th power, and that's 0.5754. And that keeps going. But we'll just leave it sitting there on our calculator. We can kind of look ahead down the road here and see, I only have one thing left, and that's multiply by 20. So since the only thing left for me to do here is multiply by 20, I'll leave that whole number on my calculator, multiply by 20, and get 11.5084. And that keeps going. In this one, we were told to round to the nearest tenth. So we'll find the 10th place. We'll look one space to the right. That's 4 or lower. So we'll round this down, and there'll be 11.5 milligrams remaining after 11 hours. So far, we did a little bit of review with evaluating expressions, kind of like we just did there. We plugged in 11 for T with solving equations. We looked at mathematical modeling by looking at linear models that had linear growth and linear decay. We looked at mathematical modeling with exponential models, where we had exponential growth, and now we just did exponential decay. Does anybody have questions about anything we've worked on up to this point? We haven't really talked any financial stuff, any consumer math type stuff yet today. Modeling sort of relates really well with consumer situations. As a big idea, modeling is really important. I just want to make sure we're comfortable with what we've done so far before we venture into the more financial looking topics that we are going to talk about today. All right, let's go forward. If you think of anything, you let me know. Simple and compound interest were two. Oh, sure thing, Shu. You bet. This one. Okay, well, we can talk about what you did. I'm not sure I'm going to love it since it came up with a different answer, but yeah, let's talk about it. Okay. Okay. I completely understand what you did. Now let's take a look at that. It is wrong, and there's a reason for it. Hopefully, I'll be able to explain why it's wrong in a way that makes sense to you. I'm pretty confident I can. Here's the thing. What you've done is you've done, you bet, you've done what you found, and let me, I'm gonna throw this down here in this corner over here because I think I can do it down there. So what you did was said, well, it's 2,500. If I find 5% of that, then that would be 125 people. And then that's going to happen 6 times. That would be true if the population stayed 2,500 the whole time. The thing is, it doesn't. At the end of year 1, we don't have 2,500 people anymore. When we start year 2, now we have these 2,500 plus 125 more. So when we start into year 2, now I have 2,625 people. And I need to add 5% of that. And so 2625 times 0.05, now we're going to add 131 people on top of there. And so I'd have to add the 131, and now I have 2,756 people. And so what you did, I understand the logic behind it. The problem is, because the population changes every year, the number of people that would be involved in the growth changes every year, and your way didn't account for that. And that's why doing it this way works. is because what we're doing is we're multiplying by 1.05, then 1.05, then 1.05, then 1.05. And that's why this is a more efficient way to go than finding the new population every year. Yes, it's exactly like compound interest. That is the perfect parallel, Sue. It's basically because when we do compound interest, we are earning interest on the money that's been added to the account. Here, the population growth is based on the growth that has already happened. And that's the thing that your calculation didn't account for. You got it. It's perfect. You got it great. That's outstanding. Very good. Very good. And that parallel is spot on. Gotcha. Gotcha. No, it's exactly the same as compound interest. Our compound interest, we earn interest on our interest. Here, our population grows based on how much it had already grown. And so that's how they're similar. Very good. That was a good discussion. That's excellent. Anytime anybody has questions, I want you to ask them because somebody else may be thinking the same thing as you, or it might just generate an interesting discussion like that one there. Awesome. Simple and compound interest came up last week, and when we look at the simple interest formula, what we see is I equals PRT. You'll notice there are no exponents anywhere in there. Simple interest follows a linear model. Compound interest, though, you'll remember, P plus 1 plus R over N raised to the N times T. That one does have variables in the exponent. So compound interest follows an exponential model. When our money's growing with simple interest, it's growing in a linear fashion. When we're investing in compound interest, it grows at an exponential rate. And we hear that thrown around a lot. It's growing exponentially. Let's take a look at what that means. The sort of contrast between linear growth and exponential growth. And simple and compound interest give us a fantastic way to look at that. Let's say we were going to invest $1,000 at 8% simple interest or compounded monthly. So this is the comparison we're going to make here. And there's one big idea that I want you to take from this, and I'll emphasize it at the end. Please don't feel like you need to scribble everything down that's on this page, because it's not like that. There's a big idea here that I'm going to share with you after we talk about it. You don't have to scramble to write all this down. But if we're investing $1,000 at 8% simple interest, then we're going to use the formula for simple interest. We're going to find the future value, and after a year, we'll have $1,080. Okay, great. That's good. I've got my 8%. If we invest that same $1,000 at 8% compounded monthly, then at the end of a year, I'm going to have $1,083. And you might think, it's $3. What's the big deal? What the big deal is because we're earning interest on our interest, over time, the changes get wider and wider and wider. For example, after 20 years, my simple interest investment is $2,600. My compound interest investment is $4,900. And you might think, it's still not that big of a difference. Okay, well, let's go out in the future a little more, because remember, with compound, with exponential growth, we're earning interest on our interest. And so let's go ahead and go out to the 40-year mark. And when we get to the 40-year mark, now that $1,000 I put in my simple interest investment is worth $4,600. That same $1,000 that I put in that compound interest account is now worth $36,000. And so what happens over time is when you hear exponential growth, that's what it means because we are building on top of what already has been put in there. When you invest in simple interest, you get this nice linear growth. Nothing wrong with that. But with compound interest, because of the exponential nature of it, it absolutely takes off at a certain point. And then, if we go to the 50-year mark here, you can see 5,000 or 54,000 is a huge difference. And no more money's been put in. This is just earning interest on the interest, the compound interest, and what exponential growth looks like. The main idea here is that exponential will grow faster. That's the main idea here, especially over the long term. But even in the short run, the exponential does grow faster. You can see after year one, the exponential growth is going to give you more return than the linear growth. One of the things I want to point out about this, and again, this isn't really a question for a quiz or an exam, it's just the truth, is as you look at this and you see what happens to your investment over time, they always tell you that, start saving for retirement as young as possible. And this is the reason for that. The longer you give that exponential growth to happen, the more it can really take off. And you can see what happens here between the 30-year mark and the 50-year mark. There's a huge increase. And that's why, if you can start saving for retirement in your 20s or even 30s, it'll make a huge difference on the back end. That's hard to do. I admit I wasn't great at it at that time. But if you can, it can make a huge difference because of the way compound interest works. And you can look at this. I mean, $1,000 at 8% and don't touch it for 50 years, and it's worth $54,000. I mean, that's, it's multiplied by 54. And because of that, Albert Einstein, one of his famous quotes that has to do with finance is that compound interest is the most powerful force in the universe. And it's because you're earning interest on your interest. It's money you didn't even put in there, and you're earning interest on it. And it really causes things to take off over time. Okay, so main idea here is comparison of exponential and linear growth. The exponential is going to grow faster. But it's also a really good illustration of some really useful financial principles. Okay. We have one more idea to talk about today, and that is the rule of 72. It's a relatively straightforward idea that says this, that an investment compounded annually at a rate of R% will double in 72 over R years. That's a whole bunch of words. Let's back up for a second there. If it's compounded annually at a rate of R%, it will double in 72 over R years. So 72 over R will be how long it takes to double. This kind of just gives us this nice little formula here. And it's a really handy approximation that if you know the interest rate, you know how long it will take for an investment to double. A sum of money is invested at a rate of 5% compounded annually. How long will it take for this investment to double? Now, one thing that could happen to you is you're like, okay, compounded annually. So I got to run straight to my compound interest formula. Hold on a minute. Read that whole question through. Make sure you're careful when you read it. And when you see how long will it take for it to double, that tells you this is a rule of 72 question, and it's a lot less work than using the compound interest formula. So the key indicators here of when do I use this rule of 72 anyway? It's when you're being asked about an investment that's going to double. Okay, sum of money is invested at 5% compounded annually. How long will it take for this to double? And according to that new formula that we just learned, 72 over R is the number of years it will take for this to double. One thing that's different about the rule of 72 compared to all the other problems we work on, this is the only time we don't turn it into a decimal. So when we're doing rule of 72, we don't convert the percent to a decimal. What I mean by that is when we plug this in to find out how many years it's going to take to double, here we have a 5% rate. We just do 72 divided by 5, and that'll give us the number of years it's going to take to double. 14.4. So how long will it take this to double? It'll take 14.4 years. Just the one thing that's strange in here is you just have to remember when you're doing rule of 72, don't convert the percent to a decimal, just leave it as a 5. 72 divided by 5, that tells us how many years it'll take to double. The calculation is very simple. The main thing is make sure you recognize it's a rule of 72 question because it said how long will it take to double, and then don't convert the percent to a decimal. I'm going to have you try one. $2,000 is invested at a rate of 7% compounded annually, rounded to the nearest tenth of a year. How long will it take for this investment to double? And again, how long will it take to double? That tells us rule of 72. I'll make a poll for this and let you try it. The key to the rule of 72 questions is identifying that it is a rule of 72 question, and then don't overthink it. Don't make it harder than it is. Let's go 30 more seconds on this, and then we'll do it together. See where we are. Not unanimous, but pretty close. It could just be making it into something that it's not. So let's take a look here. $2,000 is an invested rate of 7% compounded annually, round to the nearest tenth of a year. How long will it take to double? As soon as we read how long will it take to double, that means, hey, this is a rule of 72 question, and I know that that's just 72 over the rate will give me the number of years it will take to double. And in this one, that'll be, let's see here. Well, the rate was 7%. So if I just do 72 divided by the rate, that'll give me the number of years. 72, oops, 72 divided by 7 is 10.2857. And this particular problem said rounded to the nearest tenth of a year, so we'll find the tenths place. Look one space to the right. That's 5 or bigger, so we'll round this up to 10.3. So it'll take 10.3 years for this to double. Two keys in this question. One of them is, remember, don't convert that percent to a decimal, just leave it alone as a 7 when we do rule of 72. The other one is this. The 2,000 here at the beginning had absolutely nothing to do with the work we did in the question. It's going to be worth 4,000 at the end because it's going to double, but that wasn't part of what we had to do here. The fact that it was a $2,000 investment to start with doesn't change anything. The rule of 72 is just 72 divided by the interest rate. Doesn't matter how much money is involved. If this was 2,000, it would take 10.3 years to double. If it was 5,000, it would take 10.3 years to double. If it were 50,000, it would take 10.3 years to double because it's only about the interest rate. So that 2,000 was a distractor that was put in there to kind of throw you off, which might make it a trick question today, but not anymore. Now you know. When it's a rule of 72 question, we're just using this right here, and we're finding out how long it takes for it to double. All right, here's a rule of 72 question that on the surface doesn't necessarily read like a rule of 72 question, but I want to make sure that you recognize it as one. If you have $500 now and you want it to be worth $1,000 in 8 years, what will the interest rate need to be? Now, you might think, is this simple interest? Is this compound interest? What am I supposed to do here? Hey, wait a minute. This is, I don't think it's tricky, but I do think it's sneaky. There's a difference. You have 500 now and you want it to be worth $1,000. That means that this investment is going to double. So it's sort of an underhanded way of saying we want this to double, which means it's a rule of 72 question. So the word double wasn't anywhere in the question, but if we look carefully at those numbers, we can see what's happening. Hey, it's doubling. That's rule of 72, and that's 72 divided by the rate will give me the number of years. Okay, now what's the rest of this question? Since you tried to put one past me on this 500 turning into 1,000, what's the rest of it? All right, the rest of it is I want it to double in 8 years. What does the interest rate need to be? So this time it told me how many years I'm looking for the interest rate. Well, that's okay. There's basically just two pieces in here I don't know. As long as they give me one of them, I can find the other. This time I was given the number of years. So 72 over the rate equals 8 years. We need to solve for R. And just like we did back when we were working on some of the questions in the geometry chapter, when the variable's in the denominator like this, we've got to multiply both sides by R so that cancels out in the denominator. And now I have 72 equals 8 times R. And then the last step we'll need to do here is divide by 8 on both sides. And that 72 divided by 8 will be, that's one that's always hard for me to remember for some reason. 72 divided by 8, 9 years. Or excuse me, 9 is the rate, I'm sorry. So my rate is 9%. The key to this one is recognizing out of the gate that it's a rule of 72 question because we're starting with 500 and we're ending with 1,000. So hey, that money's doubling. That makes this a rule of 72 question. So I'm going to use this formula right here. They gave me the number of years. I'll calculate to find the rate.